He discovered Pluto, but did not live long enough to see Pluto demoted. That's why I said maybe it was a good thing that he moved on. So, To Infinity and Beyond is an exploration of humans standing here flat-footed on Earth, looking up and wondering, what is that up there? Can I ever get there? Will I ever get there? Is it impossible? What are the fits and starts that we go through in order to achieve dreams that at any one moment feel like they are impossible, feel like they're at infinity? And then you achieve it and you say, hey, I'm on a new vista and I can see far beyond anything I saw before, and to me they're now new infinities, other unattainable goals that sit before us. So, I want to impress upon you the challenges we face as scientists when we make discoveries. You read about the successful discoveries. You don't read about the failures, because nobody reports about the failures. But the failures are kind of important too. And you need to know there's some questions, for example, that have no answers. You say, what? What do you mean by that? I got one for you. Ready? Okay. Do you know this question has no answer? Did you know that? Ever thought about this? How tall are you? She's 5'4". Not 5'4.5". Flat 5'4". Just exactly 5'4". Okay. Let's see. So here you go. Okay. There's your pigtails. Are you exactly 5'4"? Well, let's go find out on the measuring tape. So there we go. And wait a minute. These lines have widths. Wait a minute. What? How do you know you're exactly anything? Are you on the right-hand side of this? Or the upper side, the lower? Are you exactly in the middle? Do you even know this? No, you don't. Because your measuring stick only goes to, at best, 1/16 of an inch, and nobody gives their height to 1/16 of an inch. You would worry about the person who tells you that. Consider also that you're about a ½ inch taller when you wake up in the morning than when you go to sleep. In some cases, a full inch taller. NASA knows this. Oh, by the way, you're taller because gravity isn't shrinking you, assuming you sleep horizontally. I'm hoping that's not a big assumption here. So gravity shrinks you, and NASA knows this. Do you know that the spacesuits they designed for the astronauts on the launch pad are typically 2 or 3 inches shorter than the spacesuits they use when they spacewalk? Because by the time they spacewalk, they've been in 0G for days and days and days. The disks expand out, they get taller, they can't fit in the spacesuit that they once were. So this goes on. How long is the coastline of the United Kingdom? And you say, well, that's a weird thing. Why is that even a question? I'll tell you how interesting that question is. There's an entire wiki page with that title. Okay? It's not just some one answer. Again, these are questions with no answers. Well, how would you measure the coastline of the United Kingdom? Or at least the main island, Great Britain, I guess it would be. So let's take a look. All right? That's not a very accurate way to do it with the 12 matchsticks. But it gets you a first pass. You take all these sticks, and then you lay them out and measure the length. That's a first pass at the coastline. But the actual coastline will be what? Longer or shorter than that? Longer, of course. How much longer? Well, let's do a better job. Let's use smaller matchsticks, okay? We use small, that's a better job. We get in the nooks and the crannies, okay? Mostly the crannies. I don't know the difference between a nook and a cranny, but that was fun to say. Anyhow, but it's missing some pieces over here. This will get a better answer than that one, but it's still going to be wrong. Is it going to be too long or too short? Once again, too short. Well, where does this stop? How short do you have to make your matchsticks to do this? Well, why don't we use a string? Then they're not line segments. Let's use a string. We can do that, and those little bitty bits that stick out. But wait a minute, let's zoom in. Okay? Wait, did your string include to go around these rocks? Are these rocks even part of the coastline? Do you even know how to think about answering that? And it doesn't stop there. Are you making your measurements during high tide or low tide? The question, how long is the coastline of the United Kingdom, has no answer. You can look it up and it'll give you an answer, but you just have to agree that that's the answer. It's not the answer, because there isn't an answer. No, there isn't the answer, there's only an answer. So don't go to one source and you get one number and another source gets another number and you want to call one source wrong and the other source right. No. Measurements always have uncertainties at all times. And in science, it's all about measurement. I don't publicly reference the uncertainties in the measurement as errors, but that is what we call it in science. Publicly, I call them uncertainties, which makes way more sense to the public's ear than these are errors, because they think you messed up in your measurement. No, you didn't mess up in your measurement. You're 5'4" with a plus or minus on there that you don't care about, okay? Let's keep going. What is the shape of Earth's orbit? You guys are coming, you know I do astrophysics. You have probably some cosmic fluency. So you tell me, what's the shape of Earth's orbit? Ellipse. Everybody knows it's an ellipse. Everybody knows that. Okay, so let me show you. We can quantify how elliptical something is. It's called ellipticity. The 0 is a perfect circle. This is a low ellipticity shape in the upper right. 0.03, it's still kind of circular looking. Finally, we're getting something that looks like a red-blooded ellipse, okay? So which of these is Earth? Earth's orbit, would you say? The top left, top left. Oh, it's not a circle, we know that. Top right. Bottom left. Bottom right. Okay. Because you were told it was an ellipse. You were told this. Okay. The eccentricity of planet Earth is the upper right diagram. The upper right diagram. If I said Earth's orbit is a circle, you'll say, no, it's not, it's an ellipse. But you couldn't pick out the ellipse that it was. All right, that's just because you didn't know, that's fine. But let's keep going. Do you know, okay? That is not how elliptical the Earth's orbit is. That is false. Yet this is displayed in a book, feeding the errors of your ways. But so even though we're nearly a perfect circle, it's still not even that shape. Why? Because that is Earth on the left, and that's the moon. The moon doesn't orbit Earth. Earth and the moon orbit a common center of gravity. So Earth is kind of jiggling like this, while the moon is going around like that. So if Earth is doing this, while it's on an elliptical path, it's doing loop-de-loops. That's not a perfect ellipse, that's a loop-de-loop ellipse. Not only that, the entire solar system is moving through the galaxy. The sun is dragging all planets and comets with it. What does that look like? We have a loop-de-loop and it's helical through space. None of these is an ellipse. So to say it is an ellipse, just no. Just, we will approximate it as an ellipse and be happy with that. But again, these are the challenges, not only as a scientist, how do we characterize that, but also as an educator. Am I going to teach all of that in one fell swoop? Or do I start out saying, Earth's orbit is a circle? Then you get an idea, we go around the sun, it's slightly off from a circle. There are loop-to-loops. There's a helix. You build on that, that's fine. But when people say, I have the right answer, that's why, while I'm entertained by shows such as Jeopardy, the idea that, here's the answer, I can't. There was one question one year. In fact, Kareem Abdul-Jabbar was the contestant, and he got the wrong answer, but for the right reasons. But they couldn't give it to him because his answer was wrong, but he was thinking beyond the question. The question was, which European country has the largest land area? Okay, which country is it? Europe, is Russia part of Europe? When did that happen? Did Russia take over Europe while I wasn't looking? Is it part of Europe? So he mentioned Sweden, and he said, how can it be Sweden? What he really meant to say was Denmark. But Denmark wasn't the answer they were looking for. They were looking for, like, was it Spain or Germany or something? But I forgot, one of those. It's Denmark. Why? Because Denmark owns Greenland. Yes! He knew this, but he got the wrong country. He was thinking it was, he was Scandinavian. But again, running around saying, I have the right answer and your answer is wrong. No, I don't play that. Okay. Also, I just did this. I tweeted this once because I had nothing to do that day. I calculated the ellipticity of the Oval Office in the White House. Okay? If you want to know. Yes, I did this and posted it. So its eccentricity is 0.6, so it's very elongated. And by the way, which means you can focus sounds in one part and hear it in the other part. Yeah, so if the president is at the desk, then the couch area here, the president can eavesdrop without them knowing. But why would they be in the Oval Office telling secrets that they don't want the president to hear? So that's a stupid example, but it would happen that way if it did. Let's do more. What is the diameter of the Earth? You can look this up. But wait a minute, are they including the mountains? Okay? Are the mountains there? The diameter, are they going to the Marianas Trench? Where's the Marianas? Is it up there somewhere? Yeah, the Marianas Trench. That's the deepest part of Earth's crust, as any geologist knows. And that's where, if you want to test your submersibles, you do it there. If it's going to implode, that's where it's going to happen, especially. Okay, so, by the way, going into space is way safer than going to the bottom of the ocean, all right? Do you know the pressure difference between your capsule and empty space? 1 atmosphere. The pressure difference between sea level and the bottom of Marianas Trench? Squash you like a pancake. So where are you going to measure the diameter? Okay? How are you going to do this? By the way, okay, if you measure us from pole to pole, it's 7,900 miles. You measure it across the equator, it's 26 miles bigger. So Earth is oblate by a little bit. There's oblate or prolate. Oblate is hamburger, prolate is hot dog, okay? And if vegans can one day give me replacement foods for that, I'm happy to include that, but they work really well right now, okay? And we're slightly wider below the equator than at the equator. So we are a pear-shaped oblate spheroid. And look at, I have it accurate to miles there. What's that about? Here's something. Earth is practically a perfect sphere. You say, no, it's not. There's a mountain sitting in front of me. What do you mean we're a perfect sphere? Well, how big is the mountain compared to Earth? How big is that? Do you know the distance from the bottom of the Marianas Trench to the summit of Mount Everest? Do you know what that distance is? Okay, any idea? 12 miles, thank you. Love you all. 12 miles. And for reference, The length of Manhattan is 13 miles. So, this, if you have any used cue ball in a pool table, it will have dings and nicks in it far greater than any surface features on Earth, on the planet Earth. And so Earth is smoother than any used cue ball. Just keep that in mind. What else? How about, what is the diameter of the sun? Ought to be able to measure that. Look that up. You should be able to measure that, okay? But wait a minute. It's a ball of gas. That's right. How do you measure the edge of the gas? Okay? Here, let's go to different wavelength of light. What's the edge of that? Yeah, you go and measure that, okay? You come back and tell me. It depends on what wavelength of light you're using. We'll give you a different answer. As a scientist, we confront this. We don't know going in that we'll have different answers, but we got to be ready for it. And not walking around saying, I have the answer. That's not how this works. You say, I have an idea. I have a way to make a measurement. And I will report the measurement and compare it with other people's measurements. They might ask the question differently. So now, I'll tell you a little bit more about data. Let's start out here. Galileo, this is a plaque of a painting of Galileo that was gifted to the Hayden Planetarium in 1964 on the 400th anniversary of his birth. It's a painting by Sustermans, Justus Sustermans, and here it is. That is hanging in the Perkin Library of the Hayden Planetarium. That is Galileo about 10 minutes before he died, looking very sad. What did Galileo do? Oh, well, in 1610, he looked up and published his observations of the night sky, including Jupiter's moons. That's interesting. The title of his book was Starry Messenger. I borrowed the title of that book from my book from a year ago. In Latin, Sidereus Nuncius. And he looked up and he saw, oh, by the way, he saw these star things drawn there. He saw them move back and forth across Jupiter. But they looked like stars. He couldn't see a disk. They were just points of light. So to him, he called them stars. And he called them Medicean stars. Why? The Medicis was his, you name it after the rich people who pay your way, okay? That's how that works. That's always been that way, okay? The Medicis. All right, which Medici? Oh, so wait, let me zoom in for folks in the back row so you get a sense of this. Yeah, so he's drawing this and tracking them with his telescope. So here's what he's doing. All right, this is on a loop, but these are the 4 brightest moons of Jupiter, and they orbit Jupiter. Oh my gosh, Earth is not the center of all motion. Stuff can go around Jupiter too. Yes, he named him after Cosimo II Medici, Cosimo, and that's not how long he was Grand Duke of Tuscany, that's how long he lived. By the way, through the early 1800s, half of all people born were dead before they turned 35. Yet all those people ate organic food. Their air was clear, their water ran pure, their game was free range. Still couldn't get past 35 on that one. Science matters, okay? This painting is by the same guy who did Galileo, hanging in our offices. So he died at 31 of tuberculosis, which today hardly anyone, possibly no one, dies of. All right, those 4 moons are called the Galilean moon. We don't call them the Medicean moons. We named them after Galileo, which I'm glad we did. So now, oh, by the way, we've discovered some more moons of Jupiter. This is a zoom out, and you get to see, so Io Europa, Ganymede and Callisto should come in next. Where are you, Callisto? There you go. Those are the 4 moons discovered by Galileo. The inner ones he couldn't see with his telescope, nor could he see the rest of these as they show up. Those are 63 moons of Jupiter, known a few years ago. But since then, we've discovered more moons of Jupiter. So here's the point. When Isaac Newton came up with his theory of gravity, it worked for the Earth and the moon, and Earth going around the sun. It worked for the planets. It even worked for Jupiter and its moons. So you got to figure out this might be a universal law of gravitation. Planets and our moon, Jupiter and its whatever those starry things are, the Medicean things, and for us going around the sun. We're testing the limits of these new ideas. This is a bust of Isaac Newton I have in my office. He's not always staring at me like that. I usually have him in the back. But Isaac Newton, my man. Again, I'm trying to get sympathy from you for what we go through as scientists and how careful we have to be. So, William Herschel, who's somehow always looking to his left. I don't understand why. He accidentally discovers planet Uranus. That's orbiting beyond Saturn. First time anyone had ever discovered a planet. Mercury, Venus, Mars, Jupiter, and Saturn are bright enough for the naked eye, and the ancients knew about it. The cavemen knew about it. So no one is credited with their discovery. Uranus was discovered by William Herschel. Except he didn't call it Uranus at first. He named it after the king. So for a while, I have textbooks from a period right in the late 1700s, and they enumerate the planets from the sun. Mercury, Venus, Earth, Mars, Jupiter, Saturn, and George. And by the way, that's the same George of the American Revolution, George. Was it the George III, maybe? Which George was that? Third, thank you. Good historian. Just calling that out. That's the same George. So we have maps, Planet George, and no, we're not calling it Planet George. So here's Uranus. Okay, so now watch what happens. We look at the path of Uranus around the sun, and it is not following Newton's laws. It's deviating. It is not behaving according to the universal law of gravitation. Maybe we found the limit of Newton's laws. Maybe they applied only out to Saturn. And Uranus is beyond the limit. People were considering this. Maybe we need a new theory of gravity to get us beyond this. All right, some other people said Newton is badass. Basically, whatever the equivalent of that word from 200 years ago, that's the word they used, okay? This is John Couch Adams' forehead, and this is Urbain Le Verrier. These are 2 brilliant mathematicians. This is from the UK, obviously from France. They said to themselves, suppose Newton's law is not in error. Suppose there's another planet unaccounted for in our equations tugging on it. That could explain it and leave Newton's laws intact. This is a very hard problem, especially when you don't have a computer, because you're not looking at the object and calculating a force of gravity at a distance. That's just a simple formula. You are asking yourself, what would have to be here for have a force of gravity act in the way that gives you the perturbed orbit? That's an inverted part of, it's an inversion problem in gravitation, and it took brilliant mathematicians to do it. They each came up with these calculations, then they sent it to Germany, to Johann Galle, and on September 23rd, 1846, the day after he received these coordinates, he went to the telescope. They said, look over here. He looked over there, and he found Neptune. Found Neptune. exactly where it was supposed to be. Newton's laws were intact. I should not be showing you Uranus here. This should be Neptune. So pretend this is Neptune, okay? Okay. So Neptune, we got a new planet on our hands. Okay, planet Neptune, discovered by math and physics. Okay, now we start tracking Neptune's orbit. It's not following Newton's laws. By the way, these things take hundreds of years to go around the sun, so we're only observing pieces of its orbit. There's uncertainties if you have only a tiny piece of the orbit. You got to wait enough time to trust your data. Okay, we look at Neptune and it's not following Newton's law. Well, we've been down that road before. There's another planet. It's got to be. And thus was born the search for Planet X, launched by Percival Lowell. Here he is looking very New England, Tweedy. Percival Lowell. He said, there's got to be another planet out there. They did the inverse calculation. They couldn't find any planet. He says, got to be there. They checked the calculations again. Look here, there's nothing there. He says, it's got to be there. So he decided to search systematically across the sky rather than just in one spot. Well, he would die in 1916, but the project had been started and was continued by the one and only Clyde Tombaugh. He died just before we opened the Rose Center for Earth and Space. And that's a good thing, because he discovered Pluto, but did not live long enough to see Pluto demoted. That's why I said maybe it was a good thing that he moved on. Clyde Tombaugh, farm boy, amateur astronomer, built his own telescope. He discovered Pluto. How do you discover a planet? You be systematic about it, and then you take multiple pictures. Separate. This is separated by a week. And so here's the same star field, and right there in the center of that dot, it moved to over there, whereas every other object remained the same. Pluto was discovered. He was famous for saying, when asked, how did you find Pluto on the photographs? And he said, oh, it was easy. There was an arrow pointing towards it. That was his big joke. Okay, so the New York Times reports on this discovery. They give it a mass. We hadn't measured a mass for it yet, but you know what mass they gave it? They gave it the mass it would need to have if it were disturbing the orbit of Neptune. It was just handed a mass. It wasn't measured that way. And over time, we continue to observe Pluto, and it's like smaller than we thought, and it's tinier, it's got less mass than we thought. And someone created a plot. They said, if this continues, Pluto will disappear. Okay, what's going on? I'll tell you what's going on. Planet X died in 1993. A paper published by Miles Standish, Jr., that's the same name of one of the names that came over on the Mayflower. Planet X, no dynamical evidence from the optical observations. Here's what he noticed, that the orbit for Neptune was obtained from many different observatories. And you cobble together the data from different time periods, lay out the arc, apply Newton's laws, and you are not getting the right answer. He said to himself, wait a minute, at the US Naval Observatory, over that 10-year period, there's a swath of data, and he checked like the log books. And he found out that they did something, like they cleaned the gearbox, they did something to the gearbox, they did something in the logbook. And he said, let me remove those data and keep all the rest. When he did that, Neptune landed right where it was supposed to be, according to Newton's laws. So here we have a case of bad data. So Newton's laws fails the first time, but then it's triumph because we get the planet. Here, it fails, but not for that. It had bad data. What are you going to do? Okay, let's keep going. The planet Mercury, closest to the sun. It has one of the most elliptical orbits of them all. And if everything were normal, it would just do this, highly exaggerated. It would just do this on the left. But that's not what Mercury's orbit was doing. That orbit is precessing. So for every loop, the ellipse, okay? I've never before been in an ellipse, but this is actually kind of fun. All right? There's some force of gravity other than the sun that's making that happen. We said, we've been down that road before. There's another planet there, close to the sun. You can't see it because it's always in the glare of the sun. We even named the planet. We called it Planet Vulcan. We named it. The astronomers were perfectly happy invoking another planet too close. So during every solar eclipse, where the sun's light is blocked out, we said, do we see anything there? None of the eclipses revealed a planet Vulcan. So this was a conundrum, but we weren't worried about it. We just kept going. Then, in 1916, planet Vulcan dies. It dies an ugly death because Albert Einstein publishes the theory of general relativity. And in this, we learn that under high gravity, Newton's laws fail. They actually fail. And it needed a new understanding of gravity brought to you by Albert Einstein in this research paper, published in 1916. So, here we are, scientists trying to make discoveries, and in the first case, the failure became an affirmation of Newton's law of gravity. In the second case, the failure was because of bad data. The theory still worked, but it was bad data. In the third case, the failure was an actual failure. We don't know this going into the problem. We do the best we can. Yes, things fail, and the press hardly ever talks about it. So these are the kind of challenges we face. And the book is all about that. From the very first thoughts we had about our place in the universe, what went right, what went wrong. And by the way, one of the strands, as I said, the DNA strands, is pop culture. So here's an example of pop culture. When we talk about the density of things, we talk about the Incredible Hulk. Okay? There he is, in case you don't know what he looks like. So here's an interesting question. Because we talk about the density of air, and what does it mean to float in air or sink within air? So density is an issue. So we talk about density in the Hulk. Movies are the scenery as you read through the book. Whenever a topic is touched by a cinematic theme, we'll go there. So let's take a look. So if you do the numbers, the Hulk is about 10 times the volume of Dr. Banner, okay? Well, if you take Dr. Banner and puff him up by a factor of 10, his density changes. What happens to his density? We're puffing him up. Yeah, it decreases. It's the same mass, but in a higher volume. So let's see what the density of the Hulk would be. Okay? So let's do this. In grams per cubic centimeter, iron is 8. Rocks are 3. Water is 1, by definition, actually. Quark is 0.2. The Hulk is 0.1. You could just kick the Hulk and he would just bounce down the road. Just see that happen. He'd be like a Macy's balloon, just moving down the street. So if he retained his density, he has to get mass from somewhere. Where's he getting the mass from? Is he converting it out of the energy of the environment? If he is, he has to suck the energy, because E equals mc squared. He has to suck the energy out of everything county-wide. All electricity would go out just for him to get the mass that he acquires. Just a little things to think about as you're going through the book. But my favorite Hulk is the credible Hulk, okay? So here he is, the credible Hulk. You won't like me when I'm angry, because I always back up my rage with facts and documented sources.